Okay, so this is lecture 10, and today we're going to be doing Reingold's theorem, which is something that I mentioned earlier, which is that undirected graph ST connectivity can actually be done in log space. It's a rather beautiful result, and in the course of preparing this lecture, I realized that what I thought you do actually doesn't work, and you need to be, there are certain subtleties that one needs to be a little bit aware of. So as a proof, like in the zigzag case, it's actually quite short. It's something that can be described very easily, but it takes, all of this takes time to sort of internalize. So I'd like to go through a slow recap where we go over the graph operations that we had, the constructions that we built last time, and so on, and then eventually get to Reingold's result. Okay, so there were basically three operations that we saw. The first was the powering operation, where you basically take your graph and you just square the adjacency matrix. And intuitively, or if you want to think of it as, taking the ith edge or jth edge out, now every edge label now corresponds to a pair, I1, I2, and it's like as if you take the I1th edge and then the I2th edge. So you're taking a two-step work. So the resulting graph is going to be on the same set of vertices, and the degree is now going to get squared, and your eigenvalues get squared. So as a result, the spectral gap becomes this 1 minus of 1 minus gamma the whole square. And it's sometimes convenient to write it in this way. I'm just writing it as gamma times 2 minus gamma. Because once you write it this way, you sort of see that the spectral gap is increasing. Because gamma is always a some quantity between 0 and 1. So 2 minus gamma is some quantity bigger than 1. So it's like saying that it is increasing by a factor of 2 minus gamma. Okay. And in terms of the adjacency, or rather the neighborhood map, where I'm just abusing notation and calling this to say that the I1, I2th neighbor of U is, you first take the I1th neighbor of U and take its I2th neighbor. So that's what this is. And you can also phrase this as a rotation map if you want, by just keeping track of what the other coordinates were. Okay, so that was the first part. And the second graph operation that we saw was tensoring, which is like you imagine having both of these graphs separately, and then every step corresponds to a step in this graph and a step in this graph. So intuitively, the neighborhood relation looks like this. I hope it's not cut off. So the neighborhood relation is like, if you start with the vertex U1, U2, where U1 is supposed to be a vertex on G and G1, and U2 is a vertex on G2, and you want to look at the I1, I2th neighbor, that's the same thing as saying you take the I1th neighbor of U1, comma, I2th neighbor of U2. Okay, so that's what this is. And once again, if you want to write this as a rotation map, you just keep track of the other coordinates. Okay, and one of the things we saw was that the number of vertices is now going to be the product of the number of vertices of the two separate graphs. The degree is also going to be the product. The eigenvalue also turns out to be the product, which means that the second largest eigenvalue will be whatever was the larger eigenvalue between the two graphs. So in some sense, the spectral gap, therefore, is going to be no worse than the worst spectral gap between the two graphs in question. Okay. And then finally, we had the zigzag product, which pictorially, this is what we were sort of saying what it is. You replace each vertex of your graph G by a cloud, and which I'm sort of just put it in green, which is like CU and CV. And the zigzag product is, of course, you set up the two graphs in such a way that the number of vertices of the second graph matches the degree of the first graph. So you can, in some sense, each of these clouds, you can sort of slap a copy of H on that, such that every vertex of H now identifies one particular edge leaving that. And you do this in some system, some manner. I mean, like for every U, you decide on some labeling of this form. And then what were the edges in the zigzag product? Well, it's all the red edges. Basically, you look at an intercloud edge, which is one of these black edges. Now, that specifies two vertices in those two clouds. Look at their neighborhoods in H and put a complete bipartite graph between the neighborhoods on this side and the neighborhood on that side. Okay, so this was what the zigzag product was. And in terms of rotation maps, it's going to be helpful to think of it as like, if you were to think of it as a code, and you want to write the code for the rotation map, what would you really do? Okay, and so just to make it easier to trace, so let's say this is U and this is the vertex A, and I'm going to call this A prime, and this is B prime, and say this is B. Okay, so so let's say you're starting at U comma A, and I want the I1, I2th neighbor. So the first thing you ask is like you ask what is the I1th neighbor of A in the graph H, and you get some A prime. Okay, forget the second coordinate for now. Okay, which means from here I end up going to this vertex. So I'm at A prime. And now I ask, what is the A primeth edge going out of U? Which is the same thing as you apply the rotation map of G on U comma A prime. That tells me this is the edge, and I end up at V comma B prime. That's what the rotation map tells me. And now I ask, what is the I2th neighbor of B prime? And maybe that is this vertex. So I eventually land up I say that the I1, I2th neighbor of U comma A is actually V comma B. And to go the other direction, I just need to keep track of the other coordinates which I ignored previously. Okay, so this is if you were to write the rotation map as code, this is what you would be doing. And we'll be revisiting this soon, because by the end of today's class, we're going to look at basically observe that this can be done using very low space. Okay. Okay, good. The key theorem that we saw from last time was this theorem of Reingold, Trevisan, and Madan. Actually, the paper proves a stronger bound than what this is, but this is what we proved in class, which was that the spectral gap of G zigzag H is at least as large as the spectral gap of G times the spectral gap of H squared. So you should be thinking of it as saying the spectral gap of G gets a hit of just gamma H the whole square. So it reduces a little bit, but you have made a big progress in terms of making the degree very, very small. Okay. And I mean, the key point was that this graph is now a graph on, ND, comma, D squared, comma, some gamma graph. So in some sense, compared to gamma of G, the new gamma is a little smaller by a factor of gamma H to the whole squared. But the key gain is that the degree has now become small d squared. We have massively reduced the degree in the process. Okay. And then we saw two graph constructions to sort of build these expander families. A family of expanders that are guaranteed to have some spectral gap. They're all some regular, and they're on increasing number of vertices. And there were two examples that we saw. The first example was you're just using squaring and zigzag together. You square it to reduce the eigenvalue and do zigzag to sort of make the degree small. And you just keep doing this again and again. And we saw that this was, in general, the tth graph in the family is a graph on d power 40 vertices. The degree is going to be capital D squared. It stays capital D squared irrespective of what t is. And you have a guaranteed spectral gap of at least a half. That was what this construction was. And we saw that, like, if you ask how much time does it take to compute the neighborhood relation, it actually takes polynomial time. It takes poly in the number of vertices, which is not a strongly explicit family, but nevertheless, it gives you one nice family to work with. Okay. The second construction that we saw was, instead of starting with a d power 4, d 7 by 8 expander, we started off with a d power 8, d 7 by 8 expander. Okay. And then we did this thing where you tensor and then square and then take zigzag. So the tensoring is like you're increasing the number of variables. You're squaring because you want to reduce the eigenvalue, but then both of these operations would have messed up your degree a lot. So you take one zigzag at the end to bring the degree back down. So, and if you work through this thing carefully and ask what is this family going to give, this turns out to be some nt, d squared, half expander. So the guaranteed spectral gap is a half. This is also a capital D squared degree graph. And the number of vertices starts looking like basically n to the d to the order t. So if you calculate this exactly, it will turn out to be d to the 8 times 2t minus 1. This is what I was hoping to do last time, but then I somehow got lost in that calculation. But if you go through this, this is what you get. Just to get a sense of, notice that this is a graph on d power 8 vertices. If you see what is this a graph on, notice that this is a graph on d power 16 vertices. Squaring does not increase the number of vertices, and then to d power 16, I'm multiplying by another d power 8. So this is d power 24. So, and then G3 will have d power 5 times 8 vertices and so on. So you can get that.
So just quick well, so this one which gave you this polylog, that was because of this T by 2.
So previously so basically gamma of GT took time whatever exponential in T.
Yeah.
This turns out to be poly in NT. Right, because NT is the number of vertices, that is also exponential. Some base is different, but nevertheless it's polynomial.
Yeah.
But whereas here,
no, I know, but I'm just saying, why did the tensoring help?
Because here, I mean, previously, in order to compute one edge relation of GT plus 1, I had to compute two edge relations within GT.
Correct.
Whereas here, I need to compute just edge relations in GT by 2 and GT by 2.
Yeah. But if why can't we do the T by 2 square?
Oh,
what was the tensoring giving us?
No, T by 2 squared, I think, will not have the sort of size that we would want, I think.
The size.
This, correct?
The
number of vertices, yeah. So this actually it takes time, actually poly in T rather than poly in 2 power T, rather than exponential in T, which is poly log in the number of vertices. Okay, and therefore this gave us a strongly explicit pattern. Okay, so this was the brief recap of what we did last time. And now I'm going to do a recap of the ST connectivity algorithm that we saw. Okay, and let me first tell you what the algorithm is and then wonder about when will this algorithm work. Okay, so flipping it around because the algorithm is easier to explain. The algorithm is this following really stupid algorithm. Firstly, what is the algorithm? So this is an algorithm for checking if S and T are two vertices that are connected in the given undirected graph. Okay, and maybe I should make sure that this is undirected. Okay. So what is this algorithm? Okay, maybe it's instead of n power 5, put some other larger polynomial. But basically, what are you doing? You just are taking a random walk of some length, and you're just waiting to see the vertex T. If you have seen the vertex T, you're going to say, okay, S and T are connected because I started the walk at S. Of course, this walk is going to tell me that S and T are connected. And if in this many steps, I don't see T, I just want to return saying, okay, S and T are actually not connected. I'm not particularly careful about what this n power 5 is. We just saw last time that for some suitable power of n, this algorithm ought to work. Okay, and let's just go back to those calculations and sort of see why did we say so. Okay, so what do we want to say? We want to say that if the graph G is nice, by that what do I mean? Look at the connected component, containing S. Okay, there is some connected component containing S. So obviously, when you're taking a random walk starting at S, you're going to stay within that component. Let's for the moment assume that that connected component is not bipartite. Okay, and I want to say if T is in this component, I want this algorithm to output the answer no with very, very small probability. The chance that I miss T must be quite small. Okay, this is what I would like to say. Maybe not for n power 5, maybe for n power 100, something. There's some polynomial for which this will work. And what was the intuitive reasoning for this? And the rough reasoning for this was that look at the connected component containing this S. That is currently a connected graph and a non-bipartite graph. which means it has a spectral gap of at least inverse polynomial. So if I run for poly many steps, the random walk will mix. And we did this thing of just imagine stopping at every n power, I don't know, n cube steps and asking, is this t, is this t, is this t, etc. Every time there is a small chance that you will find t. And the chance that you don't find it at all for n power, I don't know, that many steps was quite small. This was some calculation we did earlier. Okay. And so now what we want to do is we want to basically take this algorithm and de-randomize this. We want to say, can we remove the use of randomness in this algorithm completely? And there is a special case in which you can do this. Okay. And the special case is the following. I'm just going to use component of S in G to just refer to the connected component in G that contains S. Okay. Let's assume that it is a deregular graph, firstly, and that it is actually some gamma expander for some gamma of your choice. I don't know, 0.1 or something. Okay. And I want to know in that situation, can I actually de-randomize this algorithm? Okay. And there, what did we do? We basically said, let's imagine running the same algorithm as earlier and ask, obviously, when every time I run I'm starting with the probability P, which is completely distributed on, say, the vertex S. That's my starting distribution. I run a random walk for, say, K steps. And I want to know what is my deviation from this, the stationary distribution, which in this case is the uniform distribution. And this is something we saw last time, which is that, it sort of looks like root n times lambda to the k. So it keeps shrinking by a factor of lambda every time you take one more step. So which means if I set k to be like something like order log n, this right-hand side will become at most like 1 over. Okay. In fact, let me make it like 1 over, I don't know, 10n. Like I just choose k to be large enough so that the right-hand side is at most 1 over 10. But what does this mean? This means that if I look at the distribution after k steps, there must be some mass on the vertex t if t was reachable at all. Now, why is that? So the mass that the uniform distribution puts on t, is like 1 over capital N. If p times n power k did not put anything on t at all, then the total variation distance is at least 1 over. But I've set it up such that it's at most 1 over 10. So it better be the case that it puts some mass on the vertex t, if t is reachable, of course. If t was in this component, then it has to put some mass on t, which in other words is like saying that I know t is reachable in at most k steps. So this was a way of sort of saying that if you know that your component is an expander, then the diameter of your graph is like order log n. This is just a different way of stating that same thing. Okay, so if at all t is reachable, I know it is reachable in log n steps, like order log n steps. Okay, so now here is a stupid algorithm that we have. So I'm going to think of a path label as saying that, it's telling me which neighbor I need to take at every step. So this 1, 1, 1, 1, 1, I mean, this is like of length k. Or rather, let me just say it is of length k. So there are k ones. That's my starting. Basically what I'm going to do is I'm going to explore all vertices that are reachable within k steps. And I'm doing it in some systematic manner by which I'm saying that I'm first going to approach the vertex that was take the first edge k times. And then I will do first edge, second edge, and so on. I keep doing this until I end up with this d, which is like in some sense the last possible path you could take.
Yeah, here d is a constant.
Yeah, d is a constant. I'm thinking of d as some fixed constant. Okay, let's say 100. And what is this algorithm? It's just going to do the following. It will keep running this algorithm until this path is not everything. Okay. Maybe I should put while at the do until probably rather than while. If people okay. Anyway, so basically, what do? You look at the vertex that corresponds to start from S and follow the right path. You will end up at some vertex V. Obviously, if that V happens to be the target vertex T, you just say, yeah, I found T and I accept. Okay. And but if that didn't happen, I just increment path. And you do this in the most obvious way. I mean, go to the last thing, just change it. Like imagine this as one large number and then change it. Okay. And I do this for all possible paths of like length k. And if at the end of it I have not found t, I am guaranteed that t is not reachable. So I just say no. Okay. So this is the algorithm. And let's get a sense of how much space does this algorithm take? What do I need to store in this algorithm at all? I need to keep track of what is my current path that I'm exploring. So I'm keeping track of this path, plus maybe what is the current vertex I am on. Okay, there's some bookkeeping in order to compute this vertex V. I might have to keep track of, okay, right now I'm at this edge vertex, I need to take this edge, and so on.
When it is path, we need walks.
So
you don't care about vertices repeating.
That's a walk, right?
Yeah.
Okay, so I should be writing walks everywhere. Yeah, I don't care. I'm not going to. I can't afford to remember. Yeah. So how much space does this take? It's basically dominated by the space needed for path. Okay, more or less. I mean, plus maybe one or two extra vertices and bookkeeping, which I'm not taking. And how large is path? Okay, this is just going to take k log d. I mean, that's the amount of space I need, because a path is some element in d to the k. Okay, so there are k coordinates, each of which requiring log d bits. So it's like k log d. And we are assuming that d is a constant. K was like order log n. So this is like order log n. Okay. So in the special case, when you know that your connected component containing the vertex S is an expander, here is a deterministic algorithm running in just order log n space with just that much space that happens to correctly solve the ST connectivity problem. Okay, hope this is clear so far. So basically what we are going to do now is ask, can we reduce the general question of solving ST connectivity in an arbitrary undirected graph to ST connectivity with the guarantee that the connected component containing S is actually a nice expander. Okay, so that's what we want to do. And the way we would like to do this is there a way to expanderize the graph without messing up with the connectivity relations? Obviously, I don't want things that were disconnected to suddenly now become connected, but I want each connected component to now become an expander. Okay, and pictorially, roughly this is what I would like to do. It's going to be a bad picture, but I'll still tell you what it is. Let's imagine this graph on the left. It's currently a 3 regular graph. Okay, think of self loop as degree 1. I mean, okay, or whatever. And suppose I just do a zigzag product of this with a triangle. Okay, which is a legitimate thing because the left hand side is a 3 regular graph. I now take a triangle which is on 3 vertices, it's connected, so I do a zigzag product. What will end up happening? You will end up with some nonsense like this. So each old vertex will become a cloud. And somehow, like when you zoom out, it will look like you have basically a copy of G sitting inside, but except every edge here will start corresponding to some complete bipartite graph you put on those, and so on. And self loops here will sort of mean that there are internal connections that are happening also, and so on. But this is roughly what the graph would look like.
But you did say this, right? I mean, so the zigzag product is not commutative, is it? Or is it?
No, in the sense that it's not. I mean, it won't be compatible if you change the order. Yeah. Yeah. So okay. But the key point I want to make here is the following: that if you basically imagine each of the cloud as being a copy of your old vertex, every vertex now became a largish cloud. Okay. So now there are many, in some sense, a vertex here. There are many potential candidates of you choosing a vertex on the right hand side. Okay, but one thing that is for sure is that if S and T are 2 vertices that are not connected in G, their clouds will not be connected in H either. in some sense, the underlying connectivity structure is still preserved. It's just that there are many copies that H has, sorry, that the vertex S has. But nevertheless, nothing from the cloud of S is connected to anything in the cloud of T. So the underlying connectivity property is still preserved when you do the zigzag or you do tensor or any of these things. So this is what we are going to be crucially using. Okay. And the key idea that we are going to start off with is, let's just assume that the graph G was deregular somehow. Okay. We'll figure out how to make it regular if it is not regular. And just imagine running the previous zigzag product construction. Just do the same thing of, we'll square the graph, take zigzag, square the graph, take zigzag or something, hoping to make it a better and better expander. And hope that after some time, it will actually become a good expander. Or rather, when I mean it will become a good expander, what I mean is every connected component will become a good expander. Okay. And then I just run the deterministic ST connectivity algorithm. So, and basically this is what you need to do. The only real technical hurdle is that this is all going to be something which is like a mental thought process. You will not be able to actually make changes to the graph because you can't afford to write down what your new graph is because you're only running in log space. So whatever you are doing, you should be doing it implicitly. Okay. So all the technical hurdle is just making sure that this general idea of expanderizing a graph can actually be done implicitly, and we can then run the deterministic ST connectivity algorithm. Okay, so that's going to be what I'm going to do for the rest of the lecture. And let me give you an overall idea of what's going to happen. So like earlier, I mean, we are in fact going to follow the weakly explicit expander construction. That's already going to be good enough for Reingold's algorithm.
Because now you're only interested in space.
I'm interested in space. I don't mind running in polynomial in the size of the graph. I only want to make sure that the space used is small. So the weakly explicit graph construction is going to be good enough for this. So we'll fix the same base graph as we had in the weakly explicit. This thing, it's some d power 4, d, 7 by 8 expander. Now G is some arbitrary graph. I have no control. It need not be regular. It's just some undirected graph. So the first thing that I'm going to do is make it d squared regular, just like we would have done in the previous case. In the previous case, we started off with G1, which was basically h squared, so that it became d squared regular. But now we'll try to come up with some other method to make it d squared regular. And we will make sure that we introduce self loops in the process, just to make sure that the graph is for sure not bipartite.
So G, we are assuming is still some regular.
No. It could be arbitrary. The first step is going to be to make it regular and also in the process add some self loops. Okay, we'll add some self loops in the process. And this is just to ensure that the conditions for my previous thing were, that is, I want the connected component to not be bipartite. If the underlying G was bipartite, this is something that we have to mess with and so on. So I'm just going to ensure that I put one self loop in every vertex just to ensure that it's not bipartite. Okay, so that is G1. And from this point onwards, I just do the same sort of construction like we did in the expander construction. G2 is going to be G1 squared zigzag with H. G3 is going to be G2 squared zigzag with H. And I'll keep doing this until I get to GL, which is GL minus 1 squared zigzag with H. Okay, and spoiler is going to be that this L is going to be roughly order log n as well. Okay, that will ensure that whatever is this new graph GL, notice that it will be on some exponential at L many vertices, which is still polynomial in n. So this L is going to eventually be whatever logarithmic, and then we will run the deterministic.
Now, what is n here? N is the size of the original.
Oh, so yeah, I am assuming that the size of G, this was equal to n, and this we will run it for L equals some order log n. Okay. So in the process, your new G will have size which is polynomial in n. Okay, and we'll run the deterministic connectivity algorithm, whatever log space connectivity algorithm to check if cloud of S is connected to cloud of T. Okay. In this process, what will happen is every old vertex would have now become a larger cloud, etc. So the cloud of S is whatever is you got from S overall. And we're just going to check is anything from cloud of S connected to a vertex in cloud of T. Okay. If you think of your vertex labels as being S comma blah, it's like saying that is the vertex S comma, I don't know, 00000 connected to something that looks like T comma star. So that's one other way of interpreting this. And this is going to be the rough idea, but the key point is going to be that I can never write down any of these GIs on a tape, because doing so would mean that I'm spending polynomial in n space. I can't do that. But I have to still be able to do a random walk on GL without writing the graph GL completely. Okay, so that's going to be the primary challenge. Okay, so since we are going to be dealing with doing this carefully with low space, etc., it's good to come up with a systematic description of what I mean by running an algorithm for a certain rotation map. I mean, computing a random walk is the same thing as computing a rotation map. I mean, listen, that if I can do a rotation map, I can certainly do a random walk. Sorry, by random walk, what I meant was just choosing a certain, I don't know, rth neighbor in the graph GL. Okay, and we want to make sure that we set up we systematize the way in which we are going to talk about these algorithms so that it's clear to us that this algorithm uses this much space. So I'm going to do that in a very maybe slightly painful way, but is going to clean up what we want to say later on, which is, so this is going to be the typical setup. I have to do a rotation map for some graph GA. GA is one of these graphs that we constructed in the process. Okay. But what is there for me as input is actually just the graph G, and I don't know, I'm given say S and T, which I'm going to ignore, because as far as just computing the rotation map is concerned, the S and T are not relevant at this point. Okay, what I have written is G and S and T, and this I can't modify because this is a part of some read-only tape that I have. And I'm going to assume that there is the second tape, which is really where the input for the rotation map is written. And I'm going to make certain assumptions about how this is going to be written. So, I mean, there could be some stuff initially, but then there is going to be a u comma I, which is the input to the rotation map. And the two ends are demarcated, I don't know, maybe with some special symbol. You put a star or something. And the head is positioned at the end of the input block. But it could be the case that beyond that, there was also some other stuff. Okay, I mean, like these are things that I don't have any control over. But the fact that the head is positioned at a certain point and that there is another marked index to my left sort of tells me what the relevant input is. So u comma I is a relevant input. There is other data on the tape that I'm not allowed to mess up. Okay. And then maybe I need some extra paper, rough paper to do something. So I have some extra work tapes. This is going to be the underlying machine model. So this is what the machine is working with. Okay. What is the expectation? Like after you solve the rotation map, what do I expect this machine to do? So the first thing I want to do is the following. All the work tapes must be clean. I mean, like basically this tape, if I had written something on it, at the end of the computation, I want that to be cleaned up. So when the computation ends, there should be nothing on the work tape. But the important thing is what tape 2 contains. So I want tape 2 to contain the following thing. Okay. And this is same stuff. This is same stuff. And I want the head to be positioned here, where, sorry, we were doing rotation, right? Where rot GA of u comma I equals v comma j.
So what was A?
So A is some index. Maybe I want to compute the rotation map of GL, in which case A is equal to L. But I want to make sure that what is on this read-only input tape is only G. I don't really have access to GL. GL is all implicit. Okay. And what I want to do is I want to replace U comma I with V comma J, where V and J were the corresponding output of the rotation maps. It's just that if there were stuff to the right and the left of these marked points, I don't want that stuff to get messed up at all. Whatever is that stuff is going to stay. Okay. And throughout, we are going to keep track of our memory profile. And the memory profile will be whatever was written on the stuff, plus anything extra that you used in your workspace at any point. Like basically, it should be the case that at any point, if you freeze your Turing machine, it could be the case that maybe you have temporarily rewritten something here. You're hoping to put it back at a later point. Okay. And maybe you have a whole bunch of stuff here. So at that point, your space profile would be whatever is written on tape 2 plus whatever you have on your work tape. And I want to make sure that throughout the run of the algorithm, the space profile never exceeds order log. Okay. So it's a slightly weird description because the way we are going to run this rotation map is like initially, of course, it will be very clean. But sooner or later, tape 2 will have all sorts of other stuff written, which I truly want to ignore. I mean, and keeping track of them, like if you try to copy them onto a work tape or something, that will be too expensive for you. Anyway, when we see it, we'll see why this particular description. But I just want to make sure, is the description clear? So the head is at a certain location, which also has a marked index, let's say star. And the input goes, as long as if you keep on moving left, the next star indicates what the actual input is. So that's really what I'm supposed to be working with. But there could be stuff to its right and to its left. And I'm not expected to mess them up at the end of my computation. Maybe intermediately I do something with respect to that. Okay, is this clear?
What is this stuff going to keep track of?
Good. So basically what will end up, okay, let me just tell you what might happen. Maybe I have UA, and let's say I want to do the rotation map of a zigzag. So I have UA, I and J. Sorry, I1 and I2. So what do I want to do? I want to think of this as an input for my rotation map for H first. And then replace this with, I don't know, A prime comma J1. Anyway, actually, let me not jump ahead. We'll see this precisely. We're going to like painfully work through this calculation and then we'll see what happens. Okay, so this is the requirement of what I want when I say that I want this Turing machine to compute rotation map. This is precisely what I do. Okay, good. So let me first describe what G1 is.
Sorry, because of that, you should peek that you should have a bit confused. So U here is a vertex in GA, right?
Yeah, so technically speaking, what's going to end up happening is, this will already look like U comma A. And this J will probably look like J1 comma J2 or something like that. So, but every time I might have to do I might want to ignore the rest of the tape and just focus on something. Like in the sense that if I'm working within a cloud, my cloud index will probably be written to my left, And at that point, I don't want to mess that up. I'm doing something when I take this intra-cloud edges. Anyway, we'll see this in action.
But U and V, sorry, U is a vertex in
So,
GA, right?
No, yeah, U is a vertex in GA. And I is going to be something in, I don't know, D squared.
Sure. But this U being a vertex in GA means that U is a vertex. I mean, eventually it's
U is made up of some large tuple.
Yeah.
Right? It maybe has several components inside. Okay.
Probably has U, the original vertex in G, and then some.
And then every time you did something, you added extra coordinates in something. So
other A number of other things.
That's right. It has a bunch of other things. Okay. So let me first describe what G1 is, whose goal was to basically making G D squared regular. That's what G1 was. You started off with some arbitrary graph. All I want to do at this point is just make it regular and add self loops. Okay. And here is pictorially what you do. Okay. So let's say this is some vertex U here. And this is what you do throughout. So I'm going to copy, paste this here. And this is very similar to what we have seen earlier, which is I erase all of this and then I put new vertices on each of these spokes. And now I connect them using one cycle. Okay. So right now, let's look at the degree of each vertex. So previously, the vertex, I don't know what, it need not even have been regular. Each one has some degree. Right now, what I did was I took one vertex and replaced that with a cloud of a cycle. The new graph, notice that has degree 3, because every vertex has something in that same cycle to its left, same cycle to its right, and the edge that was going out. So it has degree 3 now. Okay, I need to get degree d squared. So what I'm going to do is plus d squared minus 3 self loops. Okay, just some way of making it a d squared regular graph. Okay, now notice that the original degree of u is sort of irrelevant. Whatever the old degree of u could have been, this graph is still d squared regular. Like every vertex now has d squared edges going out. There are d squared minus 3 self loops. There is one going to its left, one going to its right, and one going to a different cloud. Okay.
And it's not affecting reachability.
It's not affecting reachability. Okay. The underlying, the overall picture of the graph stays the same. Okay. And the first thing I want to claim is that this rotation map of G1 can actually be computed efficiently. Right now, I just told you what to put on each vertex. We can now be systematic about how are we labeling these edges. I mean, each vertex must now tell me what is my left neighbor, right neighbor, what is my 1th neighbor, 2th neighbor, blah, 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 all the way to d squared neighbor. So you come up with some mechanism. Maybe let's say this is the old cloud that we have. So this is one of these vertices. So this going to the next vertex, maybe I call that the first edge. The one going to its left, maybe I'll call that the second edge. The intercloud edge that is going out, maybe I call that the third edge. Everything else are like basically 4 all the way till d squared. So now when someone writes a certain thing on the tape and tells me you are at u comma I, so basically your input is, let's say, u comma I, and I want, I don't know, the jth neighbor. If j was equal to 1, you just return u comma I plus 1. If j was equal to 2, you return u comma I minus 1. If j was 4 all the way till d squared, you just return u comma I again. But if j was equal to 3, now you look at, well, what was the ith neighbor of u in the original graph, and then return that. So there's nothing spectacular happening here. I mean, like it's just a simple description of what, if you were to compute edge relations on this new graph, what do you do? Obviously, it's a very local operation. So if I ask you for your neighborhood relation, it's also a local computation. It's easy for you to just verify that this takes order log n space in the Turing machine description that we get. Okay, good. So this is done. And this is the main theorem. The main theorem we want to prove is that this actually extends for all GLs as well, not necessarily just G1. Okay. And we basically want to say that the space that it takes to compute GL plus 1, in fact, I'm going to be more precise here. Or, okay, let's anyway fill up this blank shortly. But basically, I want to say that this should take order log n space. As long as L is bounded by order log n, this should take order log n space. Okay, and we're going to do this recursively. Okay, so the way I'm going to describe this is I will first give you what is the most natural way of doing it. And then we'll notice that runs into trouble. Okay, there are some subtleties involved, and this is going to be the crucial point where the fact that there were things to the left of the input and right of the input which I didn't want to change, that's going to become crucial. Okay, so this is what I want to do. And okay, so the input, how is my input written? There was a read-only tape that had G. I want to compute GL or GL plus 1. Okay, that's what I want to compute. But my input read-only tape had G. And now a vertex of GL plus 1 is written here. And what does that vertex look like? Well, that vertex is going to be, it's going to be some U, which was a vertex of GL, followed by some A, which is some vertex of H. That's what a vertex of GL plus 1 looks like. So it actually is made up of a pair, U comma A. Okay. And now the edge label is some I1, I2. Because it was a D squared regular graph, which I'm thinking of as I1 and then I2. So maybe to just mark this here. So this is something in GL. This is something in H. This is something in D. And this is something in D. That's the whatever. That's what is stored on them. Okay. And the first and the last thing are marked. I do not know if there is stuff to the left and beyond the marked points. Maybe there is some extra stuff. I don't know. Okay. So basically, I've just written on the right hand side. If you were to compute the rotation map for the zigzag product, what do you need to do? I've just written that on the right hand side. I'm supposed to eventually return. What am I supposed to return? V comma B comma J2 comma J1. That's what I should return. So what should finally go on the tape is V, B, J2, J1. Because that's the rotation map output. But let's see, as a computation, what are we going to do? So the first thing I need to do is the following. What is the first step? I need to compute the rotation map for H. Okay. For that, if I want to use recursively, or rather, I want to use a rotation map computation for H. I need to write things on the input in exactly the same way that we said our specification is going to look like. Okay. So I need to have A comma I1 written on the input with the two endpoints marked off and the head at the end of I1. Okay. But fortunately, A comma I1 is already written here. So the specification for how the rotation map input looks like is whatever you want to compute a rotation map on is written on tape 2. The two endpoints are marked with some star. Maybe you put one additional marking symbol, and the head is at the end of this whatever this input is. So it indicates that this is what I am working with. Okay. So fortunately, A comma I1 is already written on the tape. I just need to put this whatever markers in the corresponding point.
So when you said that we need the data to be on a tape in that way, you didn't mean that at the whatever LH step or something, the data for GL plus 1 should be written in that way. You're saying whatever rotation map you want to compute, for that the corresponding input, if it's written in that way, then
yeah. So I'm assuming that the input for the rotation map is what is my head is pointing at something. If I keep on going to my left until I see another star, that marks what the input for the rotation map is.
No, but here, where is it specified? Sorry, go ahead.
No. I think maybe I'm also not quite sure where I'm getting stuck at this.
No, just one point. So you are saying that it seems you are going to say that let's move this star here and this star here, so that A comma I1 now is defined as written here. I just move the star. I'll have to restore things back.
Yeah.
No, that's fine. But the thing is, no. Just by looking at A comma I1, how does it's a dumb question. How does the machine understand that now you need to compute this in the, so you're saying that every A has a belonging to H somehow?
No. So that's what I will keep track of on the work tape.
That's how you keep
That's the thing I'm going to keep track of.
Because which graph?
Which graph I need to be running my rotation map on, I need to know that somehow. Right? So that I'm going to keep track on the work tape. Okay. So the first thing I do is I tell myself I am doing step 1. So I write something on the work tape that indicates that I am in step 1, I am in phase 1 of my algorithm. My phase 1 of the algorithm is going to be to execute this part. And what does phase 1 of the algorithm do? It basically keeps going to the left until it reaches A. It reaches the star. Okay. And then keep going right until you've read off U. The U part of it you've done. So what I want to do is I want to add an extra star here.
No, so the point is you also now therefore know how to go until it reads, right?
Yeah, I just keep on going left until I see star.
I mean, like, no, that is fine.
Uh-huh.
But then when you say, now, what is U?
Oh,
So there you need to remember what is L. And because, somewhere you need to
Okay,
compute
so-
that. I can see that all this is done. This is just-
so okay, maybe your point is maybe I need to keep track of what L is also,
Right.
right? I mean, like,
Yeah.
what is L currently?
Correct.
Yeah, technically that should have been a part of the input. So at this point, I sort of say that I am doing step one.
That's
Wondering if this will create an
no.
issue for me.
Because L is just a counter, right? I mean,
No, I mean in the sense that shouldn't L be given to me as input is what I'm thinking.
to make things.
Yeah, because this is an algorithm that is supposed to run GL. So that input should be written somewhere.
Then it should be
Okay, so I don't know.
describe it that way.
So okay, so then I'm going to modify things a bit right now. And I'm going to assume that L is written here. Okay, so maybe the star is present at this point and L is written.
Then you have to copy L on the work table.
Huh?
Then you have to copy L on the work table.
Yeah, I don't want to do that. So that's the whole point. I mean,
You
like,
don't want to copy L now?
no, I don't want to copy L on the work because that's going to be expensive. Because L is login bits. I can't afford to have an extra login bit for every recursive call. Then I'll end up taking log squared and total space. That's what I can't do. So yeah, so let's go through this. Let's assume that the input is given as someone wrote L, which is to tell me that I am running the rotation map of GL. Okay, and then U, A, I1, I2. Okay. So the first thing I want to do is run a rotation map for H. So maybe I have a special marker. If I say I am running rotation map on H, I just write something on the worktape. So sort of mean that, by the way, this is H. This has nothing to do with this family of graphs GL that is there at all. It's just on H. So what do I do now? I basically, because I know what, I mean, based on L, I know exactly how many steps forward I need to go because I know how many vertices are there in GL. So I go forward that many bits and then I put a star here.
No, but I just meant to do that, you need to write the way you're describing the Turing machine. Now you need to copy L onto this.
Yeah. So at this point, maybe I copy L here.
Yeah.
I compute how many, what should be the length of U.
That's all.
Okay, I compute the length of U and I go forward that many steps. Once I've got forward that many steps, I just erase this. Okay, I erase this and L. And I just put a star at this coordinate. And right now, there is something that I've written on the worktape to indicate that I am in step one. Okay, or maybe let me just write step one here. So I'm currently executing this part.
So putting a star means that you would have to move these things again a little bit.
No, let's say, like for example, I'll just assume that every character, okay, there is a marked version of that character and there is an unmarked version.
In the alphabet.
In the alphabet itself, there is a marked version and unmarked version. I just replace that character with this marked thing.
Or you just give a cell in between.
Yeah, or you just leave a cell empty at every this thing.
Finite alphabet is okay.
Yeah, okay. So similarly, now once again I move forward, I put one more star here, and this is where my head is going to end up. Okay, I've done some changes on tape 2, but I have now currently marked off A, I1. Okay, now I run rotation map for H. This is a constant size graph. I can do whatever. It's written somewhere. You can just read on the whole thing if you want. Okay. And that is going to replace this with A prime. What did I call it? A prime comma J1. Okay. So far, so good.
Maybe the rotation mapping is it's written in that stuff we had written there.
No. So the rotation map, the output is written in exactly the part you had marked out. Everything outside that should be unchanged at the end of it. If there was stuff prior to it, that stuff should remain.
You mean rotation of H?
Yeah.
That's a part of input.
So let's just assume that rotation H is sort of, no, you write it on your tape if you want. It's a constant size thing. You always keep track of it. That's never going to change.
Yeah.
Okay. That part is okay. So now step 1 is done. So now I have proceeded to step 2. Okay. Now what do I need to do? I need to run the rotation map of GL. Oh, technically speaking, this should have been L plus 1. I mean, I'm running the rotation map of GL plus 1. So L plus 1 was written. That's what I want to compute, right? I mean, like I want to compute the rotation of GL plus 1. Okay. And now once again, I need to go and adjust all of these things. So I'm going to now put a star here and move my head to this location and replace this L plus 1 with L. Because now I want to compute the rotation map of GL on input u comma a. Actually, I need to compute the rotation map of GL squared here, but GL squared is the same thing as doing this twice. So that's not going to take up any more here. Otherwise, imagine this a prime has broken up into 2 parts and then you're doing 2 different rotations. Okay. And now at this point, I run whatever computation I need to do in order to compute the rotation map of GL squared. So I run the rotation map of GL once and then run the rotation map of GL again to do GL squared. Okay. And it's crucial that at this point on my tape, there is nothing written on the tape except some finite, or rather some constant sized thing, like, this is step 2 or something like that. Even if I add a single vertex label on the tape, on the workspace at this point, it's like the new space is going to be whatever is the space required by GL plus a log n. And I can't afford to do a plus log n for G1, G2 all the way till GL. So, okay, let's just imagine that, we were sloppy and there was a copy of you sitting there. Okay.
Sorry, so are we doing things iteratively or recursively?
We are doing it recursively. I want to compute the rotation map of GL plus 1. And I'm telling you how to do that. And in the middle, I will be running recursive calls for the rotation map of GL. Okay. Step 1 involved rotation map of just H. You do some rearrangement on tape 2 and then you run rotation map of H. Now, step 2 is going to be the part where you're actually recursively calling the rotation map for GL. But at that point, I don't want there to be spurious elements written on the work tape where I say that, oh, I'm going to run step 2 by keeping track of this as my work tape. There is some extra thing that I've written. Don't erase that part at all. If I did that, notice that GL plus 1 takes space log n plus whatever GL took, which is now takes space 2 log n plus whatever GL minus 1 took. And then 3 log n plus whatever GL minus 2 took and so on. So eventually I'll end up using like log squared n space, which I can't do, which is why it is going to be crucial that I don't write anything on the tape. My tape is as blank as possible when I am calling the recursive call for GL. So at this point, the only thing that is there on the workspace is that something to indicate that I am doing step 2. Okay, that is all that is there on this thing. Okay, now you run your whatever is your algorithm for GL. It does something, and it is going to replace this with V, comma B prime. That's what is going to happen at the end of running the rotation map for this. Okay. Now once again, I'll replace this to say, okay, now I need to do step 3, which is this part. Okay. What do I need to do for that? Firstly, I'll erase all of this and I copy J1 onto this tape. I copy I2 also onto this tape and then I put I2 here. Because I need to now compute B prime comma I2. So I need to put B and I2 together. So let's just go back. So this is what it was. So what I'm going to do is I'm going to copy J1 onto my workspace.
J1, you go to the right.
Yeah. Then I'm going to copy I2 onto this space, but I'll have to do this by you copy it onto the workspace and then you start pasting it back into that cell. So this becomes I2. Okay. And then I mark this off as star, mark this off as star, put my head here, and then now run my algorithm that I have for rotation map for H. Okay. And at that point, this B prime will get changed to a B. Maybe this will get changed to a J2. Okay, this is what will happen at the end of that thing. And then what I do is I just copy whatever this J1 was. I copy that back to here. Okay, this is like the final step of this thing. I increment this L to L plus 1 because previously I had decremented L plus 1 to L. I increment L to L plus 1, remove this unnecessary stars, etc., clean up my work tape, and put my head. So this is the overall algorithm. And it's not complicated, but you just need to be careful and make sure that when you're running the recursive call, your work tape is as clean as possible. You just keep track of some bookkeeping with respect to what step of your algorithm are you doing right now. You can't even afford to keep an extra vertex label on the tape at that point. So is this clear? I mean, let me just go over this again. So this involved doing 3 steps. Maybe this is all I could have. So there was U, A, I1, I2. So I first say I'm doing step 1. Okay, I mark off this region, put my head here, and now I call the rotation map for H. Okay, which changes this to an A prime and changes this to a J1. Okay, and now I want to run step 2. What do I do in step 2? I first have to decrement this L plus 1 to L, and then remove the stars and maybe put a star here. Move my head to this location, and now run rotation map of GL. Okay. And when you're running rotation map of GL, I'm going to crucially use the fact that there were stuff to the right of my tape and to the left of my tape, which I don't want to mess up. Okay, because that is there for something that I need to do afterwards. Okay, so that is still written on that tape. So I run GL right now. So this is going to become V comma B prime. Okay, and after you do V comma B prime, you once again have to adjust all of this. So I copy J1 and I2, and then I put I2 here. Again, erase all of these stars. Okay, call H again. So that is going to become some B comma J2. And then I copy this J1 that I had stored back into this place. And then readjust all the stars. Increment this L back to L plus 1. Put the head here, erase everything, and then say, okay, now I'm done. So this is what all we need to do in order to compute one rotation map on the graph GL plus 1. Okay. And the key point is that the max space used. Okay. So notice that I want to compare this with whatever happened for GL, whatever space you used for GL. I want to know what is my maximum profile that I see. There are some parts where I was doing some computation for H, during which time there was something written on the workspace. Like I had written some extra stuff. Like maybe I copied some, I1 and I2 or whatever. But the point is that is, so in some situations, I had some order log n things written on the work tape. Maybe it was less, I don't care. When I was running rotation map in H sort of computations. That is some constants. I mean, that doesn't require any recursive calls at that point. Okay. And then there were other situations when I was running a rotation map of GL. At that point, what was written on the work tape? There was only some constant sized information. to just keep track of the fact that I was in step 2 at that point. Okay, so whatever was the space I used for GL plus order 1. And it is crucial that this order 1 is not order log n. Because if it were order log n, if you run this through, you will actually end up getting that the space used for the rotation map is actually log squared, which I can't do. Okay, and because of this, this overall is just order log n plus L. So either you're going to be dominated by keeping track of this, whatever, the stack information, or, like when you were running H, you had some bookkeeping information that was stored. So maybe that took nothing. But overall, order of n plus log n is perfectly fine. So as long as L was order log n, computing the rotation map also takes order log n space. Sorry. Okay, is this okay so far? It's a clever algorithm. It's not very complicated, but it's just keeping track of the fact that when you were running rotation maps of G, there are certain things you should keep track of, but in some sense that is not changing in the path of the recursive call. So you just restructure your memory usage correctly to make sure that you don't just randomly store copies of variables when you don't need to. Okay, so then finally, we did all of this, and we are hoping that this will eventually lead to running our deterministic algorithm for expanders. So it better be the case that after running this for log n steps, the final graph GL that we have has some constant spectral gap. Okay, so that's going to be the last computation that we need to do. I want to know what is the spectral gap of GL. And obviously, when I mean spectral gap of GL, what I mean is choose a component and I ask what is the spectral gap of that component. Okay. Now, what is the spectral gap of G1? What can you give as a lower bound for the spectral gap of G1? Now, G1 was basically you took your graph, I just put a cycle on that and then put self loops. The only guarantee I have is that it's a connected non-bipartite graph. So it has some poly-ND spectral gap. Okay, just because of the fact that it is connected and non-bipartite. And now let's just ask ourselves, what is going to happen for the spectral gap of GL plus 1 for maybe larger L? So for L equal to 0, we know that it's like 1 over poly ND. But for larger L, what is it? By our, what is that called? The zigzag, how the spectral gap varies. Notice that it is gamma of one of the zigzag things times gamma of H the whole squared. So it was like gamma of GL squared times gamma of H the whole squared. Okay, which I'm going to write this as let me use gamma L rather than writing gamma of GL all the time. Let me use gamma L to indicate the spectral gap that you had for GL, whatever was your guarantee on spectral gap. And I wrote it as gamma L into 2 minus gamma L into 7 by 8 the whole square. Okay. And I want to somehow claim that as L becomes larger and larger, obviously spectral gap is increasing. But I would like to say that in log n step, the spectral gap becomes a constant. Initially, the spectral gap was tiny. The spectral gap is just this much. And I'm hoping that GL for L order log n is already like a constant. Like the gamma of GL is a constant. Now, what do we know from our previous calculation? If gamma L is guaranteed to be at least a half, then I know for a fact that gamma L plus 1 is at least a half, because this is the calculation we did when we were constructing these family of expanders. Okay. Now I want to know if gamma L is less than half, what can I say?
So you want to look at that factor 2 minus.
Yeah, exactly. So I want to say what is gamma L plus 1 in terms of gamma L now. So it is gamma L into 2 minus gamma L, which in this case is at least 3 by 2. Times some 7 by 8 the whole square. Okay, and if you just look at this calculation, 3 by 2 into 7 by 8 the whole square is just a little bigger than 1. Okay, it's like 1.1 or something. It's 1.14, some nonsense. But the important thing is it's a constant factor larger. So it's one of these things where if the spectral gap was really small, doing one step of it actually massively increases the spectral gap. It's just that this increase, of course, starts saturating once your spectral gap has already become large enough But the whole point that we are trying to argue is that sooner or later your spectral gap will become large enough. And this thing says as long as you are small, you will increase by a large factor. So obviously this cannot keep happening forever. It has to stop soon enough. So basically, this tells you that gamma L plus 1 is at least as large as the min of these two quantities. 1.1 times gamma L or half. Right? I mean, like if gamma L was already like half, then it stays half. Otherwise, I know it increases by a factor of 1.1. So this means that in terms of gamma naught, or rather gamma 1, like the first guarantee that you have, after L steps, either I have become 1.1 power L times what I started off with, or at some point in the process, I have already hit half, at which point I'm going to stay at least a half. Okay. And now, obviously, if you choose L appropriately, notice that both sides is going to be at least a half. So for a suitable choice of L, which is like order log n, you are guaranteed that the graph GL actually has a spectral gap of at least a half. Okay. So this implies that when you run this for order log n steps, that you're looking at the graph GL, that graph is guaranteed, every component of the graph is guaranteed to be a non-bipartite graph, and it's actually a half expander. And now this is Reingold's algorithm. You basically run your deterministic algorithm on this graph. Okay, what you do is you first compute what is the L that you need, some guarantee, so that GL is a half expander. You write that down. That graph GL has some diameter K, which is also like order log n. You write that down. Okay, and now you think of your S tilde as like one canonical copy of S in the cloud of S. So you call that maybe S followed by all zeros or something. And then you just enumerate through all paths. You look at all paths of length. This should be D squared probably, because this is a D squared regular graph. So you run through all paths until that point. See if you have found anything in the cloud of T. If you found something in the cloud of T, you accept. Otherwise, you just move on to the next path. If after enumerating all of these paths, you still didn't find the cloud of T, then you basically say, okay, T is not reachable. And the space used in this above algorithm is clearly, I mean, when I'm running this rotation map, there is something I need to store on the tape, which is what path am I currently on? Like, what is this path index I'm exploring, or some initial bookkeeping? All of that is like order log n space. Plus whatever I need to do, to actually run the rotation map of GL, which we saw is also going to take order of L plus log n space. And so overall, the space used is just order log.
You have to do this over all possible this thing,
All possible paths, yeah.
All possible S comma the cloud thing.
So I start with say S comma 0,
and then you go,
and I just check is V looking like T comma something.
Right.
That is how I reach the cloud of T.
No, but I mean, like, you need to check from not just S comma 0, but S comma D square. Right? Because I mean, you want to find that whether something, some S comma some coordinate reaches T comma some.
So this one is actually also good enough, because in the sense that
there is something that we will.
yeah, I just want to know, is this cloud connected to that cloud? Or maybe you think I need to do this for all of them?
No, I was thinking that to be safe. It's not
okay, maybe to be safe, you run through all possible stars here and see if you ever reached a possible cloud vertex on the other side.
That surely works.
That surely works. I think this should also work, but I mean, because if S and T were not connected, nothing in this cloud should be able to reach anything in that cloud.
No, that is true. But the point is, there could be, it cannot, what you're trying to say is that if there's something in S is reachable, then it is reachable from every vertex, in particular from S comma 0.
Yeah, that's what I want to claim. Okay,
clear.
Okay, maybe just to be safe, you just try all possibilities for this also.
So if we ensure that S has a self loop at every vertex in this.
Oh yeah, you just put a self loop on every vertex in H.
Why does that make sense?
Because then it will somehow make sure that if I think if u comma a is connected to v comma b, then u comma a prime.
What?
That's how you are, I mean, you go.
No, in the sense that it can't be a single edge. You will still have to find a long path to go.
Not a long part, one step, like you go to a different cloud and come. Right, if A and A prime are two vertices that are adjacent in edge. And so the way we are adding edges is that we look at this black edge and connect, like put a complete bipotate node here.
You're just saying, I see, several you're just saying, H is just one component, right?
Edge is just a thing, yeah.
It's a connected, therefore it should not matter once you put the cell.
Yeah.
I think that's yeah. Okay, but I mean, it really doesn't hurt us to just try out all possibilities here as well.
I mean, I was just thinking why.
Edge is something we can choose. Right? So,
Yeah, it's just something we can choose.
It is an expander with one cup.
So, okay, so I mean, like, worst case, you just try out all possibilities here. It doesn't really matter. Okay, and this is the full description of Reingold. So it's a beautiful algorithm to. Okay, so okay, so this is all I wanted to say for today, and this is something that I didn't plan on doing. I thought this is something that I will not do, but since Mrinal brought it up last time, I feel like
today's class.
I'm done with today's. No.
Oh,
in the next class, I actually thought I will start with codes, but I think I'll spend one lecture on doing these spectral specifiers, which is
with the resistance.
yeah, it's a. So, but I'll be doing the easier version, which is by Daniel Spielman and Nikhil Srivastava. There is a subsequent version of Joshua Batson, Spielman, and Srivastava, which require more. It uses these interlacing polynomials and so on. That will require a lot more stuff. By the way, I think Piyush covered it in one of his courses. I think those videos are also up. So that's what I will do in the next class. I'm hoping that this will give some answer to your thing, but in the sense that it's still randomized. It's not a deterministic way of reducing this, but we'll see that in the next time. And in the process, I have to introduce something called graph Laplacians, which is another important matrix, just like the adjacency matrix or something. There's also the Laplacian matrix, and the SS spectral specifier thing will actually go via the multiple SS. Yeah. Okay, so let's